Hi, in this video, we want to take a look at Chapter 3 of Fundamentals of Biostatistics by Bernard Rosner. This is a Cengage textbook, and we're going to be looking at probability. All right, so the big idea here is that when I want to decide based off of data, what I'm going to do, I'm going to get a mathematical model that will tell me a probability. If that probability is small, then that mathematical model probably does not connect correctly with the data I see. All right, so if I look at my data, I look at my model, and when I put them together, I get a larger probability, they probably jive together. If I take my data, I take my model, I put them together, and I see a very small probability, then that model with my data probably don't connect well. So I probably need a different model. All right, so in addition to describing data, we might want to test specific inferences about the behavior of data. So here's a hypothesis. Women who have their first child after the age of 30 are more likely to develop breast cancer than those who have their first child before 20. Okay, sample size. All right, so for the study, we're going to have 2,000 women, and they're all going to be between 45 and 54 years old. And 1,000 will have had their first child before age 20, and 1,000 will have their first child after age 30. All right, so now this is a limited sample size, so it's possible that we could have something going on. Maybe by happenstance, I end up, selecting 20, or I end up selecting 2,000 women in the population that are just different from the rest of the population. And so it might be that my results are not conclusive. And it could be that the results I have don't reflect the true population because it's really a small portion of the entire population of interest. Now, the sample size could be increased to, let's say, 10,000 women. However, the apparent difference in the rate of breast cancer occurrence may still be due to chance. So no matter what we do, there's always a chance to have a fluke in my data that makes it so that my data does not represent the total population. To set a framework for evaluating occurrence, we introduce the concept of probability. And so here, we're trying to address the chance of things just going in an unexpected manner with probability. All right, so here we have the probability of male live births during the period of 1965 to 1974. And so we have each of the time periods, number of male live births, total number of live births, and we can see the empirical probability of a male live birth is about 0.51, 2 or 3. So the probability of live male birth in 1965 was 0.512. In 1965 to 69, it was 0.51248. And then in the last range, it was 0.51268. The empirical probabilities are based on finite amount of data. The sample size could be expanded indefinitely and increased. We could get more precise estimate of the probability obtained. So the point of this slide is that there is like a true empirical, or there's a true probability of a live male birth. Now, these numbers are only estimates of that true probability. So this is my best estimate of what's going on, but you'll see that there is a little bit of fluctuation. It's not very big, but there is a fluctuation in the value from year to year. The sample space is a set of all possible outcomes, and an event is any set of outcomes of interest. The probability of an event is the relative frequency of the set of outcomes over an indefinitely large or infinite number of trials. So the probability is how likely we are to see a particular event. And real life experiments cannot be performed on an infinite number of times. Hence, probabilities are estimated from empirical probabilities obtained from larger samples. Theoretical probability models may also be constructed from which probabilities of many different kinds of events can be computed. Comparing empirical probabilities with theoretical probabilities enables us to assess the goodness of fit of probability models. All right, the point here of the second half of the slide is that if I'm using data, I truly don't know what's going on. Honestly, anytime you're using data science statistics, you don't know what's going on. If you knew what was going on, you wouldn't be doing statistics. All right, so what we're doing, we're using a data to fill in the gap between what's going on and what we can see. And we use theory to help bridge that gap also. The probability of an event is always going to be between 0 and 1, including 0, including 1. If outcomes A and B are two events that cannot both happen at the same time, then the probability of A or B is equal to the sum of the probabilities. For example, let A be a person who has normotensive diastolic blood pressure. B is a person with borderline diastolic blood pressure. All right, so you can't have both. You can either you're normal or you're borderline on this. So the probability of being normal or borderline is going to be the sum of these two because there's no overlap. The two events are mutually exclusive if they cannot both happen at the same time. All right, so let's use some probability notions. All right, so this curly braces is used to, it's set notation in mathematics, and we're saying this is the event that we're interested in. That's how we describe it. A union B is the event that either A or B occurs. All right, you see this symbol, it looks like a U, stands for union. Okay, so the event that A or B occurs. All right, so this region represents event A, this represents event B. A or B, A union B is both of these together. Now here we can see A and we see the B, and we can see that there's a region that overlaps. Well, A union B is everything in A, including the intersection, everything in B that's not in the intersection, because if I want to look at the total region and one shot, this area is both in A and B. So there's kind of like a duplicate aspect of it. All right, so A intersection B, you see this upside down U, I call it an N, that is intersection is the event both A and B occur. All right, so for example, let's say that A is the event that someone's driving a truck. B is the event that someone's driving a red vehicle. The intersection is the person's driving a red truck. All right, A bar, this is the complement. All right, so this is everything that's not in A. So if A is a truck, the person's driving a truck, the complement of A is driving anything other than a truck, a car, a scooter, a motorcycle, a semi, anything like that. So for example, if A is where the number is less than 90, the complement is the set of all numbers greater than or equal to 90. If A is occurring, then its complement cannot be occurring. If the complement of A occurs, A cannot occur. All right, let's talk about the multiplicative law of probability. All right, A and B are called independent if the probability of A and B is equal to the probability of A times the probability of B. All right, so let's say the probability of A is 1/10 and the probability of B is 1/5. The probability of both happening, if they're independent, is just the multiplication of it, and we see it's a 2% probability. If we have multiple events and they're independent, then the probability of all of them occurring is the product of all of these together. All right, two events A and B are dependent if the probability of A intersection B, there's a typo here. I couldn't get my version of the document to correct it, but there's a typo here. This should be intersection. A and B are dependent if the probability of A intersect B does not equal the product of probability A times probability B. All right, so if I'm dealing with a continuous random variable, if I have a continuous random variable, is it where any number is possible, uh, you know, in a range of values, then the probability of any exact value of infinitely long decimal precision, the probability of that exact value is going to be 0. However, there exists a notion that certain ranges of values are more frequent than others. We'll get into that when we get into distributions. This notion can be quantified using the concept of probability density functions. The probability density function of the random variable x is a function such that the area under the density curve between any 2 points A and B is equal to the probability that the random variable x falls between A and B. All right, so what this is saying, if I want to know the probability of A, so the probability that we view a number between 90 and 100, the probability of being between 90 and 100 is the total area underneath this curve between 90 and 100. So if I was to shade in the region where the letter A is sitting, that area would correspond to the probability of seeing a blood pressure between 90 and 100. The total area under the density curve over the entire range of possible values is going to be 1. Remember, probabilities add up to 1 every single time. All right, so areas A, B, and C are approximately the probabilities of being mildly, moderately, and severely hypertensive. The probability distribution function has large values in the region of high probabilities and small values in regions of low probabilities. All right, so up here, you see that this peak of the function is here. This tells me that we're most likely to see values close to 80, even though any particular number of infinite decimal precision has a probability of 0, we still have a greater likelihood closer to 80. All right, the addition law of probability. If A and B are any events, then the probability of A or B is equal to the probability of A plus the probability of B minus the probability of the intersection. And this is, once again, a typo. That should be equal. This is an equal sign. All right, so what's going on? Why do I have A plus B minus intersection? Check it out. If I take the probability of A, I've got these two regions. I have this part and the intersection. Take the probability of B, I have this region, and I have the intersection again. If I add A plus B probabilities, I'm going to have a double count here. This subtraction makes it so that I have the intersection only one time in my calculation. Now, if events are mutually exclusive, then the probability of the intersection is 0. And in that special situation, the probability of A union B is equal to the probability of A plus the probability of B. But you just need this formula. This should be an equal sign. I can't fix this. All right, so now for independent events A and B, the probability of A union B is equal to the probability of A plus the probability of B times 1 minus the probability of A. So this is attempting to simplify it. I feel like it doesn't simplify the situation better. what they're doing is in that previous formula, they're taking the probability of A intersect B and converting that to multiplication, then factoring to try and make it easier. I would just do the multiplication. All right, so two mutually exclusive events, A occurs and B occurs, and B does not occur. And so we can also expand that out. So this formula here, so remember this should be an equal sign. Probability of A plus probability of B minus the probability of the intersection. I can expand this to have more events. So I have probability of A or B or C. That's going to be the probability of A plus probability of B plus probability of C. Now, if I was to go through and scrutinize that overlapping aspect that I talked about previously, but now I've got 3 on there. So I'm going to have intersection of A and B, intersection of A and C, intersection of B and C. So I'm going to have, these guys are going to be duplicate counting. So I'll subtract them off. Now, if I was to go through and scrutinize what's happening, I would see that the intersection of A and B and C was subtracted off 1 too many times. And so there, I just want to add it back on. Easy peasy, lemon squeezy. All right, so now let's take a look at conditional probabilities. All right, so the quantity A intersect B divided by the probability of A is defined as the conditional probability of B given A. And we'll write it this way. This is B given A right there. So what we're saying here is that we know 100% certain that A has occurred. Once we know that A has occurred, what is the probability that B will occur? All right, well, if A and B are independent events, then the probability of B given A is equal to the probability of B, which is equal to the probability of B given the complement of A. If 2 events A and B are dependent, then the conditional probability is not going to equal the probability of B. All right, so let's think about a more concrete example. Let's say there's a probability that a human being will be greater than 6 feet tall. Okay. Now, what's going to happen to that probability if instead of just saying any human, we say the person is male? Well, the probability is going to increase. So now what if we say we know that the gender is female? Is that probability going to be greater or less than the general population? Well, it's going to be less. All right, so what's going to happen is that we get a more precise understanding of our probability when we condition on some other knowledge. All right, now in epidemiology, the relative risk of B given A is the probability of B given A divided by the probability of B given the complement of A. All right, this comes up a lot in disease modeling. The reason why we use this mainly is that we can get good solid estimates off of this and using empirical probabilities. If A and B are independent, then the relative risk is 1. If A and B are dependent, then the relative risk is not 1. The more the dependence between events increases, the further the relative risk will be from 1. Total probabilities rules. For any events A and B, the probability of B is equal to the probability of B given A times the probability of B plus the probability of B given A complement times the probability of A complement. If event B occurs, it must occur either with or without A. So either we're in A or we're in A complement. The probability of B is going to be equal to the probability of A intersect B plus the probability of A intersect not A. Okay, so if I take this and I start playing around with stuff, I use the conditional probability formulas and I'm alter the conditional probability so that I don't have a fraction, multiply both sides by the denominator. then we see that the probability of B given A is equal to the probability of A times the probability of B given A, and the probability of B intersect A complement is equal to the probability of A complement times the probability of B given A. That should be A complement. And now I'm going to take these formulas where I have the complement hat on here, and I'm going to plug them in to here. So this goes into this formula, replace that. This, with a hat on that, goes into here, and then boom, I get this statement about B with regard to A and A complements. The unconditional probability of B is the sum of the conditional probability of B given A times the unconditional probability of A plus the conditional probability of B given A not occurring times the unconditional probability of A not occurring. Lots of words to describe this little equation. The probability of B is expressed in terms of two mutually exclusive events, A and A complement. In many instances, the probability of B will need to be expressed in terms of more than two exclusive events. So here we have more than two exclusive events going on. The set of events is exhaustive in at least one event must occur. So here I'm breaking it up into all the different possibilities. We're going to let this be mutually exclusive and exhaustive events. So we know that one of these is going to happen, and there's no overlap. The unconditional of probabilities of B can be written as a weighted average of the conditional probabilities of B given the whichever event of A happens. And so here, the probability of B can be rewritten as a probability of B given the A event times the probability of the A event. And let's run some addition. The generalized multiplicative law of probability, if all of these A's are arbitrary, mutually exclusive events, then, actually, no, I don't need exclusive on that. So if these are arbitrary events, any events at all, then the probability of all of them occurring is equal to this chain of conditional probabilities being multiplied together. And so these are not exhaustive, or they don't have to be, and they can be exclusive or not. Okay, so why do we care about the rules that we just talked about? It works out that if I know the probability of A given B, but I want the probability of B given A, if I have it flipped on which one I want and which one I have, Bayes' rule gives us a way to turn it around, put it on its head, and do the calculation. Guess what we want. The predictive value, positive, of a screening test is the probability that a person has a disease given that the test is positive. All right, so tests make mistakes. Also, it's possible that when you go in for a diagnostic test, it's not actually giving you the correct thing. So here we are interested in, I just came up positive for a test. Do I actually have the disease? Now here, the predictive negative of a screening test is the probability that a person does not have a disease given that they have a negative test. So I go in for my COVID test. It comes up negative. I want to know the probability that I actually do not have the disease. A symptom or set of symptoms can be regarded as a screening test for a disease. Higher the positive value of the symptoms, the more valuable the test will be. Clinicians often cannot directly measure the positive value of a set of symptoms. However, they can measure how often a specific symptoms occur in disease and normal people. Sensitivity of a symptom or a set of symptoms, the probability that the system is present given that a person has a disease. Specificity of a symptom or of a set of symptoms is the probability that the symptom is not present given the person does not have the disease. False negative is a negative test result when the disease or condition being tested is actually present, and false positive, a positive test result when the disease or condition being tested for is not actually present. All right, so sensitivity, this is an important concept. This is the probability that the disease, probability that the system is present given the person has the disease. So we are conditioning on that they have the disease. Specificity is a probability that the symptom is not present given that the person does not have the disease. So for a symptom to be effective in predicting the disease, the specificity and sensitivity must be high. And so New York Times article, probably over a decade at this point ago, did an analysis and showed that, if I remember correctly, that just because you came up positive for prostate cancer on the PSA test did not mean that you had the disease. So if it was a negative, you could be very confident that you did not have prostate cancer. But if it was positive, you were like, well, I'm not 100% sure. So the informative value was lopsided depending on what the result was. The level of prostate-specific antigen in the blood is frequently used as a screening test for prostate cancer. All right, so let A be the symptom and B be the disease. The positive value, so here is positive, is the probability of B given A, and here we're using Bayes' theorem to rewrite this and flipping the conditional probability aspect. And so we can rewrite this as the sensitivity times X divided by sensitivity times X plus 1 minus specificity times 1 minus X, where X is the probability of B, which is the prevalence of the disease in the reference population. Similarly, if I'm interested in the negative value, specificity times 1 minus X divided by specificity times 1 minus X plus 1 minus sensitivity times X. And so here, both of these, we're just taking Bayes' rule and rewriting it to incorporate sensitivity and specificity. So generalized Bayes' rule, we can make Bayes' rule a little bit more flexible to take on multiple states, multiple diseases of interest. And here is the fraction written out. All right, so now Bayesian inference is an alternative definition of probability and inference. It rejects the idea of definition of probability, sometimes called the frequentist definition of probability, theoretical concept. Bayesians conceive of two types of probabilities, prior probabilities and posterior probabilities. The prior probability of an event is my best guess, my best understanding of the observance of an event's likelihood in the absence of data. So this is my belief of the likelihood before I see my data. This may be a single number or a range of values, or possibly a model, a probability distribution. A posterior probability is where I take that prior and I incorporate it with observed data. So prior is prior to the data, posterior is after the data. So the posterior probability of an event is the likelihood that an event will occur after collecting some empirical data. It is obtained by integrating information from the prior probability with additional data related to the event in question. All right, so there's two major schools of statistics. There's the frequentist and there's the Bayesian point of view. Both are good ways to tackle problems. The Bayesian point of view gives us a very complete picture of what's going on with our data. There's some downsides with that, is that I need to have good assumptions about the theoretical constructs that we pull in. If I have poor assumptions, then my model is going to be crap. The frequentist point of view doesn't suffer from as many assumptions. So there's advantages and disadvantages both ways. Find out what your stakeholders want, do it that way. Biostatistics uses Bayesian statistics a lot. All right, now the receiver operating characteristic curve. I used this yesterday at work, by the way. All right, this is a way to check to see if I have a good correspondence between my measurements of what I've got in real data and the model that I've got going on. All right, so a test may provide several categories of response rather than simple positive or negative results. In some cases, the results of the test are reported in a continuous variable. In either case, the designation of a cutoff point for distinguishing a test result as positive versus negative is arbitrary. All right, so here we have ratings of just over 100 CAT scan images by a single radiologist versus true disease status. And so here we have several possibilities. We want to evaluate, this range of values, how well does it correspond to the actual disease states? All right, so here we've got definitely normal, probably normal, questionable, probably abnormal, definitely abnormal. We have a range of values that the radiologist could give. All right, well, we want to see does the values here correspond well with the actual disease value? All right, so when do we decide to make a call on treatment or further evaluation? If we want to be really careful, we could do it when there's probably normal. If there's severe side effects of treatment, we might wait until definitely abnormal. It depends on the situation. And so since there's more of a subjective decision, we don't have a hard cutoff to evaluate things. We'll pull in the receiver operating characteristic to evaluate the quality of these measurements. All right, so now we have sensitivity and specificity of the radiologist's ratings according to different test positive criteria based off of the previous table. So sensitivity and specificity, you will notice that as sensitivity goes down, specificity goes up. All right, so this tells us that we're getting, as my rate of positives are decreased, my rate of negatives goes up. And you'll notice that there isn't really it's not a linear relationship. As one goes down, the other one will go up, but it's not exactly, if I subtract a little bit here, I get exactly that amount over here. All right, so to display the above data, we construct a receiver operating characteristic curve, ROC, which is a plot of the sensitivity versus 1 minus specificity of a screening test, where the different points on the curve correspond to different cutoff points used to designate test positive. Okay, so when I look at the ROC, first thing I want to do is I look at it and I compare it to the diagonal line going from 0, 0 to 1, 1. I want to see this as far above that line as possible. Ideally, this curve would go all the way up to this corner here, and then it would go here. It would form a perfect square if I had perfect data. All right, the more area underneath the curve, the better the situation I'm in. Now, what this is saying, this dot, this dot, this dot, what these are doing, these are giving us candidates for cutoffs for when we would say, hey, I need to start doing a further intervention. And this tells us what my sensitivity and specificity would be at each of these points. When we set up our cutoffs, If I don't have other information, what I'm going to do, either I'm going to take the point that gives me the largest sum value, or I'm going to take the point that's closest to this corner here. Those are the two major ways to go about it. All right, prevalence and incidence. The prevalence of a disease is the probability of currently having the disease, regardless of the duration of time one has had the disease. Prevalence is obtained by dividing the number of people who currently have the disease by the number of people in the study population. Okay, cumulative incidence also refers to an incidence of a disease. It's the probability that a person with no prior disease will develop a new case of the disease over some specified time period. All right, so in summary, probabilities may be calculated using addition and multiplication laws. Independent events are unrelated to each other as opposed to dependent events. Conditional probabilities and relative risk may be used or to quantify the dependence between two events. Sensitivity, specificity, and positive values are used to define the accuracy of screening tests. The receiver operating characteristic curve is used when designating the cutoff points for test positive versus test negative arbitrary values. Bayes' rule may be used to compute the PV of screening tests. And Bayesian inference, we specify a prior probability for an event, which after collecting data, we modify with a posterior probability. The posterior probability is our up-to-date post-data view. And that's it. That's all I've got for you. Take care and goodbye.